Okay, so in this video we can learn how to define the Fourier series of the function f of x. To define the Fourier series of f of x, function must be some certain kind. The first is the periodic function. So what is the definition of periodic function? A function a function f of x is said to be periodic is said to be periodic function if for some non-zero constant, so it must exist as some non-zero constant p such that f of x plus p is equals to f of x, means the value of f of x repeats for every value after some p quantity if the function satisfy this condition, then we can call that kind of function as a periodic function. So how the graph looks? The graph of this periodic function, consider for an example, if you take for sin x, so the sin x curve looks like this. So from 0 to pi, 0 to 2 pi is a one cycle, and from 2 pi to 4 pi other cycle. So the value of this function, that is the curve, will repeat for every interval 2 pi. So this is the one cycle, and the from 2 pi to 4 pi it will this is the second cycle. So the graph of the periodic function is translated by p units, means the same graph, that is this graph, this portion is shifted by p units, means it is translated by 2 pi units. So next is that here some p is there, so that p is known as where p is called period of the function f of x, and in general the function is said to be periodic function by applying the same property iteratively. We can redefine that as x plus np is equals to f of x if the function satisfies this condition, then the function is periodic. So for all the values of x in the domain, and where n is a number which is belonging to the natural number, or it might be the integers. So the examples of periodic functions are, so we can look into a few examples. So first is the f of x is equals to sin x, and the second one is f of x is equals to cos x. So if we consider f of x plus 2 pi, which is equals to sin of x plus 2 pi, so we can write sin of x plus 2 pi is a sin x. So we got the same function f of x. Therefore f of x is equals to sin x is periodic function of period 2 pi. Similarly, If we consider f of x plus 2 pi in the case of cosine function, f of x plus 2 pi is equals to cos of x plus 2 pi. So we get again cos x, we got it as f of x. So therefore f of x is a periodic function of period 2 pi. So if the function is a periodic function, then only we can express it as a Fourier series expansion. So along with this, the function has to satisfy few certain conditions for the existence of the Fourier series, that is called Dirichlet conditions. So that is called Dirichlet conditions. So what are those? There are three Dirichlet conditions. So one is that for the existence of Fourier series. First is the function f of x, the given function f of x must be periodic function. Second one, so means it has to satisfy the condition, that is f of x plus p, or f of x plus np is equals to f of x. Then the given function is periodic function. Next is the function f of x. The function f of x must exist at all the points, means the functions f of x is continuous in the given interval, means where the function is defined in the given interval, and r. So otherwise that and r. So f of x must have finite number of discontinuities. Finite number of discontinuities. So means the value of the function must be defined at everywhere. So otherwise, if it is not defined, then it has only the finite number of discontinuities, means the value function might not be defined at only few set of points. Next is the third one, f of x, means the given function f of x must have only a finite number of maxima and minima in one period or in the given interval. So it must have only a finite number of maximum values and the minimum values. The last one is f of x must be integrable in R over one period. So it means the integration of modulus of f of x into dx must be less than infinity. If all these conditions are satisfied by the function, then we can define the Fourier series. If any one of the condition fails in these Dirichlet conditions, then the Fourier series of the function f of x does not exist. Then we can see what is that Fourier series. So let f of x be a function defined and domain or interval are defined in the interval from 0 to 2 pi, then the Fourier series of f of x is defined as. So how the Fourier series looks? So now f of x is equals to the Fourier series is given by a naught by 2 plus summation n runs from 1 to infinity a n into cos nx plus summation n runs from 1 to infinity bn into sin nx. So be careful here. We are defining the Fourier series for the function where it is defined in the interval 0 to 2 pi. The interval must be careful. We need to take care of the interval. Next is if we observe, this is the series expansion of the three functions. One is, we can write this as a naught by 2 into 1 plus summation n runs from 1 to infinity a n into cos nx plus summation n runs from 1 to infinity bn into sin nx. So here it is the series or combination of three function. One is 1, other one is the cos nx, and other one is the sin nx. These three are mutually orthogonal functions. Orthogonal functions. So here we will use the orthogonal property of 1 cos nx and sin nx to determine the coefficients a0, an and bn. So those are the coefficients and are called Euler coefficients. So where whatever the coefficients we got a0, an, bn are called Fourier coefficients, are also known as Euler coefficients. So whether we can call it as either Fourier coefficients or Euler coefficients. Now we can define those. How these A naught, A n and are given? A naught is given by the formula 1 by pi. Integration runs from 0 to 2 pi f of x into dx, and a n is given by 1 by pi. Integration runs from 0 to 2 pi f of x into cos nx into dx, and the last one bn is given by bn is equals to 1 by pi. Integration runs from 0 to pi f of x into sin nx into dx. If we observe this Fourier coefficient or Euler coefficient, it has the terms cos nx and sin nx. So now we can list out few standard values which we'll use recursively, which we will use oftenly or recursively in the problems. So consider the first one, cos n pi. So take cos n pi for different values of n. If the value of n is equals to 1, if n equals to 1, we will get cos 0. Cos 0 value is 1. If n equals to 2, sorry, if n equal to 0, cos 0 is 1. If n is equals to 1, we will get cos pi. Cos pi value is minus 1. For n equal to 2, we will get cos 2 pi. Cos 2 pi value is 1. And for n equal to 3, we will get cos 3 pi is equals to minus 1. And for 4, we will get cos 4 pi. Cos 4 pi value is plus 1. Now, if we observe for n equal to 0, and for n equals to 2, and for n equal to 4, we got the value as 1. So we can write, so its value takes two values. One is 1 if n is an odd number. So if n is an odd number. So next is if you, sorry, if n is even number. And if you observe odd number, cos pi is equals to minus 1, cos 3 is equals to minus 1. And if we consider one more, for 5, we will get cos pi pi. Cos pi pi value is minus 1. So at n equal to 5, the value of cos pi pi is minus 1. So we can write it as minus 5 if n is a number. So we need to remember in the problems cos n pi is equals to 1 and cos n pi is equals to minus 1 when n is even and when n is odd. So here we need to careful. So n is an integer number. An integer number. If it is a real number, so this doesn't work for real number. So be careful. So doesn't work for n is real numbers. So that is, we can take one example for n equals to 1 by 2. So we'll get cos pi by 2, the value is 0. So this is the case where we can apply cos n pi is 1 and minus 1. Next is the second function, is the second important thing is sin n pi. So if you take n and sin n pi, so for n equal to 0, we'll get sin 0 value is 0. For n equals to 1, we'll get sin pi. Again, its value is 0. For n equal to 2 pi, sin n pi becomes sin 2 pi. Again, its value is 0. So it goes on as we take the value of n in number. That is only for the integer. So we can write sin n pi is equals to 0 for all values of n. So which is belonging to the integer number z. So therefore we need to be careful in using the sin n pi as 0 and cos n pi as plus 1 and minus 1 depending on the value of n. Depending on the value of n. With these two standard values, the limit substitution in the integral formula, that is in the Euler coefficient, it will be make us easy to evaluate. So in the next session we can solve few examples for the Fourier series.